is.
All right, video 81. All right, we're going to party at video 100. It's coming, March sometime.
Mm-hmm.
All right, we're going to talk about sample proportions. This is the beginning of a new unit, Mr. Lewis. Put it there. All right, we got this. All right, what's this all about?
Well, sample proportions. It's figuring out. Basically, you're taking your sample, and you want to know, is your proportion that you just got in your sample true for the whole population?
Cool. So we might be interested in like what proportion of people support Mayor Emanuel in Chicago,
right?
Or what proportion of people are Republican or Democratic, etc. So we take a sample to find out.
Right.
All right. So here's a simple example, just to get us going. Suppose that 35% of Foreman students are freshmen. If we take a random sample of 40 students, what fraction would we expect to get that are freshmen? Like, what would we expect to happen when we do this?
Well, we'd probably expect that out of that 40 students, 35% of them would be freshmen.
True. Right. So it turns out that if you do this, the proportion you get is going to be centered around 0.35. So could you mark in the mean? And this is one of the big reasons why we study normal curves. So when we take a sample and we look at the proportion of the sample that are like freshmen, it's going to have a normal distribution around the true value. So you're right. On average, we'd expect it to be 0.35.
Right.
Now, what's important is how close to 0.35 do we expect the samples to be? How accurate?
Right.
So when you take one group of 40 students, it might be 0.37. 37% are freshmen. You take another random sample, it might be 28%. So they're going to be distributed around the true value. Okay, so we're going to calculate. There's a formula for the standard deviation for this.
Okay.
So over here, could you write mu and put a little subscript for p hat?
Mu of p hat.
This means the average of our sample proportion. P hat is a sample proportion equals 0.35. So on average, our sample proportion is going to equal the true proportion. All right, here's a formula for the standard deviation. So maybe you can put a sigma with a subscript p hat. The standard deviation of our proportion is going to be square root of pq divided by n. It's the square root of all of that. We'll explain more in class kind of where this comes from. All right, so in this case, it'd be the square root of 0.35 times 0.65 divided by 40. So let me do that real quick. All right, it equals 0.075. Okay, can we label that in our normal curve? So this is a measure of how close the estimates will be, how spread out they will be around the true value.
0.075.
So that means, remember, 68% are within one standard deviation. So 68% of the time, we'd be within 7% of being correct. So it's not that accurate, but
no.
We'll talk about how to make it more accurate later.
But you got it. Okay.
So find the probability that p hat is within 5% of the true value. So that would be the probability. And put parentheses. That 0.3
0.3
is less than or equal to p hat is less than or equal to 0.4. All we did is take 35% and add or subtract 5%.
Yes.
So this tell me, if we go and take a survey of 40 students, what's the probability that we're right within 5%? Okay, so we're going to use normal CDF.
Yes, we will. Bringing it back.
Yeah. Always popular.
Bring it back. Back again.
The lower limit
is 0.3.
Yep. The upper limit?
0.4.
The mean?
Is 0.35.
And the standard deviation is 0.075. All right. we do this sample. There's a 49.5% chance we're within 5% of the true value.
Yep.
I know we don't know the true value, right? So, but here we're assuming it's 35%.
Yes.
All right. Now, within 20%.
Ooh,
I hope we're within 20% of the true value.
That's going to be a big number.
Yeah. So let's see. I'm hoping that if we go and take a sample of 40 students, we'll at least be within 20% of the true value.
Right.
So again, this would be normal CDF. It would be in between 0.15, right?
And 0.55.
All right, there's a 99.2% chance, thank heavens. If you're more than 20% off, that's pretty pathetic.
Yeah.
Now, the way we make it better is you sample more people.
Right.
So we only sampled 40 students. So if we sampled 100, it'd be better.
Mm-hmm.
All right, so important idea that if we take a sample, the proportion we're looking for is going to be centered around the true value, and we know the standard deviation. So if we took a lot of samples, we can tell how spread out they would be.
Yes.
All right, let's see an example. All right, actually, here's the fact. We're going to pause for a minute. So here's the fact of what we just did. I don't know why there's dollar signs above the P. It didn't translate well.
No.
From one program to the other.
Those are supposed to be hats.
Yeah, P hat. All right, so this is kind of what we just used. If we take a random sample and calculate the proportion, like the proportion of a freshman, they'll have a normal distribution centered around the true value. Could you circle that P? That represents the true proportion. So on average, our estimate will be around there.
Mm-hmm.
And then this is the standard deviation. That's the formula we just used to calculate it. All right. Now, there are some conditions for this to be true.
Yes.
We'll worry more about this later. But in order for the normal model to be valid, these things are going to have to be true.
Right. It's got to be randomized.
Yeah, like a random sample.
Because if you didn't randomize it, you'd sit there, you just pick out all freshmen, and you get a huge skewed curve.
Yeah.
All right.
If you sample without replacement, like you're not going to call two people twice.
Right.
So that means usually it's going to be without replacement. Then your sample size has to be less than 10% of the population. For instance, in this case, we picked 40 students. That's less than 10%.
Yes.
Okay, of forming population. Then there are these two facts down here. These are all have to be true for the normal model to be valid. We'll talk about more of those later.
Mm-hmm.
All right, here's the example. We're going to do one example and then kick it to the journal. It is generally believed that electrical problems affect about 14% of new cars. An automobile mechanic conducts diagnostic tests on 128 new cars on the lot. So he's taking a sample of 128 cars.
Yep.
Think of all the new cars that are made of that brand. He's taking a sample of 128. All right, and he's checking what percent have the defect.
Mm-hmm.
Well, it's going to have a normal distribution.
Yep.
Around the true value, so around 0.14. So maybe he checks the cars on the lot. It might be 15%, 16%, 13%. But if we keep taking samples of 128, it's going to be distributed around the true value.
Mm-hmm.
On average, he's going to be right.
Right.
Okay, now we should put in the standard deviation.
Yeah, we should.
So to calculate that, sigma equals square root of PQ over N. Which is 0.03. Better than last time. It's a smaller standard deviation.
Right.
Smaller standard deviation, the better. That means the values will be close to the true value. All right. So what is the probability that in this group, over 18% of the new cars will be found to have electrical problems? That'd be bad.
Yes.
If the true population is 14%, his sample is 18%.
So we want a probability that P hat is greater than 0.18.
You got it. Let's do it. So lower limit, 0.18.
Mm-hmm.
Upper limit, infinity, right?
Mm-hmm.
The mean, 0.14. Standard deviation, 0.03. There's only a 9% chance. Okay.
9%.
Yeah, so it'd be rare. If you had 18 cars, or 18% of the cars with defect, that'd be rare.
Yes.
All right, what's the probability that p hat's within 2%? So that'd be the probability.
Of?
P hat, so go from 0.12.
Mm-hmm. Less than.
So we just took the true value, 0.14, and subtracted 2% and added 2%.
Mm-hmm.
All right, so what's the probability that our sample is going to be that accurate? All right, so normal CDF, lower limit's 0.12, upper limit 0.16. U, all right.
It stays the same.
49.5%. Kind of like last problem, oddly enough.
Yes, it is.
But this is within 2%, so it's a pretty good chance, 50-50 chance, that our estimate will be that close to the true value.
Mm-hmm.
All right, let's find the probability that our estimate is going to be within 5%.
Okay. Well, we have P.
Yes.
And 0.09
Mm-hmm.
less than or equal to P hat less than or equal to 0.19.
Yeah.
And what does that give us?
90%.
0.90.
Yeah, so pretty good. We take a sample of 128 cars and find the proportion that are defective. There's a 90% chance that's within 5% of the true value.
Mm-hmm.
Getting better than before.
Yes, it is.
All right. Now, I know this is a lot of new stuff, but let's see if you got it. Sketch the distribution. Use the formulas we gave you for the mean. On average, it's going to be the true proportion. So on average, it's going to be 0.12.
Yep.
Then calculate what the standard deviation would be. And then you can use normal CDF to answer the parts B and part C.
Uh-huh.
Is that your dog?
No.
That's one cool dog, man.
It is. It's kind of like Dr. Dog.
It looks like dogs that would live near Wrigleyville, man. All right. See you next time.
Yep.